Welcome students. So next derivative. So we already learned about rate of change of quantities and tangent and normal. So today we will discuss increasing and decreasing functions. Like nature of the function, is it increasing or is it decreasing? So here I am taking a graph y is equal to f of x. Now if we check this graph in this interval, if we take an open interval here, so in this interval if we increase the value of x, then we can see here the value of fx will also increasing. Okay, so as x is increasing, fx is also increasing. Now draw any tangent at a certain point. Here I am taking this point and drawing this tangent over here. So if this angle will theta, then dy dx is slope of the tangent, that is dy dx is tan theta. Now look, if we draw tangent at any point on this interval, so what we will find? We will find this theta will always belongs to 0 to pi by 2, that means in a first coordinate. So in first coordinate tan theta is always positive. So tan theta is greater than 0. So from there I can say this dy dx is greater than 0. Now this type of functions where as x is increasing, that time fx is also increasing, this type of function is called increasing function. So here is the definition of increasing function. A function fx is defined on this open interval a comma b is said to be increasing if x1 less than x2. That means two values I am taking where x2 is greater than x1, then f of x1 is also less than equals to x2. Maybe these two values are equal or fx is smaller than f of x2 for all x1 x2 in this open interval. That time we will call the function is increasing function. Now another is there, that is strictly increasing function. That means if this function fx is strictly increasing in this open interval, that means for x1 less than x2, f of x1 is always less than f of x2. That means these two values are never equal. Always f of x2 is greater than f of x1 for all x1 x2. So next here I am graph. Here also I am taking this graph y is equal to f of x. Here I am taking this open interval. Now look, whenever I am increasing the value of x here, the value of fx is decreasing. Okay, so as x is increasing, fx is here decreasing. Now here I am taking this point and drawing a tangent here on this curve. So if it is making angle with the positive x-axis phi, then what is dy dx? Dy dx is given by tan phi. Now look, if we draw tangent at any point on this interval to this curve, so if we find that this phi, this angle will always belongs to pi by 2 to pi. That means it is greater than pi by 2. That means this phi is in second coordinate, and in the second coordinate tan phi is less than 0. Tan phi is less than 0. So dy dx is also less than 0. Now this type of function we called decreasing functions. So here is the definition of decreasing function. So if x is defined on this open interval a comma b and it's said to be decreasing for this x1 less than x2, f of x1 greater than equal to f of x2. That means x is increasing but the functional value is decreasing for all x1 x2 in this open interval. So for defining decreasing or increasing functions, we will consider a particular interval. for a particular interval we can define the function as increasing or decreasing. Now another definition is strictly decreasing function. So what is strictly decreasing function? So for function f of x in this open interval a comma b is strictly decreasing if the value of x is increasing, but this value of f of x is decreasing and it is never equal to, always this is greater than, that is f of x1 greater than f of x2 for all x1 x2 belongs to this open interval a comma b. Now if we find this type, somewhere it is moving upwards, then again from this point it is downwards, again from this point it is again upwards, from this point it is again downwards, and again from this point it is upwards. So if I draw this tangent at these points from where the nature of the graph is changing, so look these points, if we draw the tangent it is parallel to the x-axis. So according to the parallel condition for the tangent, the dy dx at these points are all 0. So now take this any point into this intervals. So if we find this, for this first interval it is dy dx is greater than 0 since this angle is less than 90 degree. Now for this point dy dx is less than 0 since this angle, if we consider, it is greater than 90 degree. So for all the parts we can check the nature of the functions, or we can say we can check the nature of dy dx, is it greater than 0 or is it less than 0. So this type of functions we called neither increasing nor decreasing, since somewhere it is increasing, somewhere it is decreasing, again it is increasing, again it is decreasing. So in a particular interval, if we find the nature of this curve or function is like that, somewhere it is increasing, somewhere it is decreasing, then we will call this type of function is neither decreasing nor increasing. Let's check some problems. This function is given, this is a polynomial function, x cube minus 3x square plus 4x. You need to show that this is strictly increasing function on R. Now look that this function is a polynomial function. So if we differentiate this function, so what we will find? F dash x. So differentiating this function with respect to x, we will find f dash x. Now if f dash x is greater than 0, that time we will call the function is strictly increasing. If it is not, then we can't say the function is strictly increasing. Now what is f dash x? F dash x is 3x square minus 6x plus 4. Now simplify this equation. What we will find? 3 into x minus 1 the whole square plus 1, which is always greater than 0 since the square term is there, plus 1 for all x in R. So therefore we can say f dash x is greater than 0, hence the function is strictly increasing function on R. For each and every value of x in R, the function is strictly increasing since it is always greater than 0. Now if we check the curve, so from here also you can say the function is always increasing function. So moving to the next problem. Here I am taking exponential function. We need to show that this exponential function is strictly increasing on this set of real number R. So you have to show that it is strictly increasing. So we can show it in two different ways. If the derivative is greater than 0, or we can choose x1 x2 and show this the functional value is also increasing. So take any two points x1 x2 in this set of real number such that x1 is less than x2. That means x1 is always greater from. Then x1 less than x2 implies e to the power x1 less than e to the power x2, since e is greater than 1. So if we take power to e, so it will always follow this property. So what we will find? F of x1 is less than f of x2. So for x is increasing, the functional value is also increasing. So from here we can say that for all x in R, that is x1, x2, I am taking here any arbitrary point. So for all x in R, I can say the function is strictly increasing, since it is follow the definition of this strictly increasing function. Now if we check the graph, so here also we can say the function is strictly increasing function. Now check function real number greater than 1. A is a real number greater than 1, then the function a to the power x is strictly increasing on R. So same process, just take 2 points, 2 arbitrary points x1, x2 in R, such that x1 is less than x2, that is x2 is greater than x1, that is I am taking the value of x is increasing, and if we can show the functional value is also increasing. Since a is greater than 1, here I am taking a is greater than 1, so any power we can take to a, it is always follow this property. For x1 less than x2, a to the power x1 is less than a to the power x2. So from here I can say for the functional value is also increasing. As x is increasing, the functional value is increasing for any arbitrary 2 points x1, x2 in R. So the function is strictly increasing function. Now here I am taking sin x, and we need to show it is strictly increasing on this 0 to pi by 2. So if we differentiate this function sin x, what we will find? F dash x is cos x. Now in this interval 0 to pi by 2, open interval, that means in first coordinate. In first coordinate cos x is always positive and not equal to 0. So from here I can say f dash x is greater than 0. That is, for all x in this open interval 0 to pi by 2, we can find this f dash x is greater than 0, hence the function is strictly increasing function. So if we check the graph from 0 to pi by 2, it is, we can show that this function is increasing function, so it is moving upwards. So check this next one, that is strictly increasing on pi by 2 to pi. So we have to show that the function sin x is strictly decreasing on pi by 2 to pi. So now if this function fx, we differentiate it, then f dash x is cos x. Now what is cos x? Cos x in second coordinate, it is negative. So cos x is negative in this open interval pi by 2 to pi, and it is non-zero also, since I am not taking this 2 points, I am taking just open interval, I am leaving this point pi by 2. So we can find f dash x is less than 0 for all x in this open interval pi by 2 to pi. Hence we can say the function is strictly decreasing function on this interval. Now if we check this graph also, we will find the graph is moving downwards in this interval pi by 2 to pi. So moving to the next, here you need to show the log function is strictly increasing on 0 to infinite. Means for the positive real numbers, the log function is increasing function, strictly increasing functions you need to show. So if we use this concept of derivative, that is dy dx is greater than or less than 0, if we can show the f dash x or dy dx is greater than 0, that time the function is strictly increasing. So the log function is fx is equal to log x is given. Now if we differentiate this function with respect to x, so what we will find? Dy dx, that is f dash x is 1 upon x. right? Now if this is 1 upon x, so for any value of x, this is greater than 0. So in this interval 0 to infinite, this f dash x is always greater than 0. So from here we can show that the derivative of this function is greater than 0 for this interval. So it is strictly increasing, since it is following the definition of strictly increasing function. So if we check the graph, you can here check from 0 to infinite, the graph is always increasing graph. Next, here is your homework. These questions are given. These are very easy questions. Now we have solved for a to the power x. You need to show this is strictly decreasing for a to the power minus x. A to the power x we already show. For a greater than 0, you need to show a to the power x is strictly decreasing for a in between 0 to 1. E to the power 1 upon x is also strictly decreasing for x greater than 0. And these two functions are given. You need to show the function is strictly increasing function, and here you need to show the function is increasing function. So any problem or any queries are there, you are free to ask. Thank you.